there's only one kind of unit cell, which is a number line. It's a length. In 2D, I told you that there are 5 different kinds of unit cells. All of them are some kind of a parallelogram. In 2D, I also told you that the new symmetry operation that you see really is, well, you see more rotations. You don't just see a 2-fold rotation. You also see a 3, 4, and a 6. Do you ever see a 5-fold rotation in 2D? Have you ever come across a 2D tile with a 5-fold rotation? Have you ever seen something called a Penrose tiling? 5-fold rotation, 5-fold rotations. It's called a Penrose tiling. Penrose tiling. And the thing about a Penrose tiling is it's not a crystal. I would recommend you look it up. There are beautiful Wikipedia pages, etc. on this. Penrose. The thing about a Penrose tiling is that they're not crystallographic. They are not compatible with a unit cell. So we don't study them. So you have 2, 3, 4, and 6-fold tilings, 6-fold rotations. You have mirrors, you have glides in 2D. You also have centering. One of the 5 different unit cells has this process called centering, which means the atom in the corner goes to the center. So that's 1 in 2D. In 1D, you have 7 line groups. In 2D, you have 17 plane groups. In 3D, I told you that the new symmetry operations are, what is this called? It's a roto-inversion. A rotation plus an inversion around some central point. It's called an axis of inversion, or a center of inversion. A rotation plus a center of inversion. This would be 4 bar. 4 bar because it's a 4-fold rotation. That's a rotation by 90 degrees. But then there is this inversion around the center. Okay? So you have roto inversions that you don't have in 1 and 2D. The other thing you have in 3D are screw axes, and we started talking about that. So screw axes, imagine that you have an axis, and we typically take this along the Z, or it could be the crystallographic C-axis. Okay? And when we look down the projection, that tells us the sort of rotational symmetry. So if I take, okay, I told you that the screw axes are 2, 1, 3, 1, 3, 2, 4, 1, 4, 2, 4, 3, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5. 6, 5. And these guys are pairs. These guys are enantio pairs, meaning one is left-handed and the other is right-handed. One is left-handed and the other is right-handed. So if I take, for example, let me take the 6-2 screw axis. Okay? For the 6-2 screw axis, what am I going to look like? So firstly, how many translations do I have to make every time along the z-axis for the 6-2 screw? That's 2 divided by 6 or 1 divided by 3. So I go up the z-axis in steps of 1/3, 2/3, 1. Okay? It's 6-2, which means it has already a 2-fold symmetry. It has a 2-fold symmetry. So if this is z is equal to 0, let me actually again use the letter R here. The letter R here. Then in the 1/3 level, at z is equal to 1/3, and let's go clockwise. Z is equal to 1/3. It's going to be it's going to have a 3-fold rotation. So that means because it's a 6-2 screw. Sorry, it's a 6-2 screw. It's going to have a It's going to have a 6-fold rotation, but it's a doubled object. So a 6-fold rotation would be a rotation by 360 by 6 is 60 degrees, right? So if it goes 60 degrees, it basically looks something like it looks something like this. And then if you go up 2/3, so this is a rotation by 60, but this is also has to be rotated on the other side because this object looks like this. And then if I go again, it looks like this. And this z is equal to 2/3, and then it returns to z is equal to 1. So it's basically an object like this that goes up to 1/3, then goes up to 2/3, and then comes back to the original position. Okay? And if this screw, which I just described as going clockwise along this direction, is 6/2, then 6/4 is going counterclockwise along this direction. So they're like opposite threadings. If one follows a right-hand rule, the other follows a left-hand rule. Okay? So if one threads in this way, by the way, in the labs, how many of you work in labs? You don't? No? You do? You do? You do? You do? Do you work in a lab? Do you ever see a left hand? Do you ever tighten things like this? How do you tighten something? Do you go clockwise from on top or counterclockwise from on top? Have you ever learned to say lefty, loosey, righty, tighty? So you tighten like this, right? Do you ever tighten in the opposite direction? So that would be a screw that is the opposite handedness. Do you ever tighten in the opposite direction? No? No? You do. When? Hydrogen bottles. You know, oxygen bottles, all gases, oxygen, nitrogen, etc., argon, tighten normally. Hydrogen tightens the other way. And the reason is they don't want you to mix these bottles. They don't want you to accidentally connect a hydrogen bottle instead of, say, an argon bottle. Right? So they make it, it needs a special threading. So if one of them is right screw, the other is left screw. So the 4/2, 6/2, 6/4, 6/3, these are all funny because they're not a single thing that goes around. It's already an object. So the 6/3 screw already has like triangular symmetry. Okay, and then it goes up 3/6. So it goes up only halfway. So let's draw the 6/3 screw. The 6/3 screw looks like this, and then halfway up it looks like this, and then all the way up it looks like this. Okay, so here R again R I didn't write it properly, did I? What am I doing? No, let me put it on this side. Let me put it like this. R, and then back to z is equal to 0. So this would be 6/3. So threefold rotation, translate by 3/6. So I would recommend that I have to post a bunch of notes. I will post some connection links to screw axes, but I will recommend that you look at all of them and be familiar with them. Okay, by the way, 6/3 will not have a left and right equivalent. Okay, 6/3 doesn't matter which way you look at it. But 6/2, 6/4, 6/1, 6/5, 4/1, 4/3, 3/1, and 3/2. So, by the way, where do we find handedness in nature? We started talking about this, I think, in the last class. Where do we find handedness? As I told you, Jean-Baptiste Biot in 1825 discovered handedness in crystals of quartz, in crystals of pure SiO2. Okay, he discovered that some crystals, if you looked at their external shape, they looked like an object that looked like the mirror image of some other crystals. So, you know, right and left hand are mirror images of each other. You cannot superimpose them, right? What do we mean by superimpose? They're not congruent objects. Are they congruent objects? Are my two hands congruent objects? You know, can you explain why they're not congruent? See, they're not congruent because this hand is now dark on top. It's the top of the hand, not the palm. If they were congruent, I'd be able to put them like this and they would overlay on each other. Okay? So these are not congruent. So things that have opposite screws, opposite are enantiomeric pairs, have a handedness, left and right. So these quartz crystals had handedness. Then, of course, in the history of handedness, Louis Pasteur played a very important role. He came along much later, and he was working with crystals of tartarates, salts of tartaric acid, which he was working with the wine industry. And in fact, even today, people actually use a combination of copper sulfate and lime. It's called Bordeaux mixture because he worked in Bordeaux in the wine industry. And they use Bordeaux mixture. Even today, they apply it to grape plants to prevent fungal growth. So Pasteur was working with tartarates, and he was able to, by hand, separate crystals that looked like they were mirror pairs. When he put them into solution, he found that the solutions of one rotated light in this direction, and solutions of the other rotated light in this direction. Okay? But to go from optical activity, the fact that if you take plane polarized light, it gets rotated, to go from there to what the atomic structure is, turns out to be a giant challenge. So it wasn't until the 1950s that this problem was solved, because standard X-ray crystallography will tell you there's a 3-1 screw or there's a 3-2 screw. It won't tell you which it is. You will have to decide. You will have to guess. You will just have to arbitrarily say, I'm calling these right-handed and I'm calling these left-handed. This is exactly what was done with sugars, because natural sugars, they're called D sugars. And natural amino acids are called L amino acids. D for dextro, which means right-handed. L for levo, which means left-handed. But the initial assignment was completely random. Okay? It turned out that the guy who did the assignment on the sugar, a guy called Emil Fischer, a famous German chemist, picked correctly. He was right accidentally. He had a 50% chance of being right, and he was right. But he picked wrong for the amino acid. Okay? In the 1950s, special crystallographic techniques were developed that could tell left from right. Until that time, crystallography suffered from this problem it's called Friedel pairs. So crystallography, when you do a crystal structure, I'm sure many of you have done some X-ray diffraction. Am I correct in assuming you've done a little bit of X-ray diffraction? A little bit? Well, you know the technique though. You know Bragg's law. You know that the X-rays come in, they go out from the crystal. You measure the angle at which you see intensity. Many angles you see no intensity, at some angles you see intensity. Those angles you measure, you see the intensity. The problem with the intensity, and you know also the X-rays come from HKL planes in the crystal. If you look at Bragg's law, 2D sine theta, it's DHKL. It's parallel sets of HKL planes. But the intensity information doesn't tell you whether it's plus H plus K plus L or minus H minus K minus L. So you don't actually know, you can't, and that's the same logic applies, you can't tell left from right-handed. They'll both give you the same intensity. So you need special crystallographic techniques to tell. So with a little bit of practice, I'm going to assume you're going to understand what screw axes are and how to identify. If I give you a screw axis, you should be able to say, I see a object with threefold symmetry, but it's going halfway up, so it's a 6-3 screw, etc. It's not maybe not trivially easy, but it'll come. But like so many things, I would argue that you don't learn crystallography, you just get used to it. Okay? Great. With that, we now have all the symmetry elements that we need to look at the 230 space groups. And of course, we shall go over each of them one by one, right? No, wrong. We will not do that. In fact, there's a famous textbook of solid-state physics by two guys called Ashcroft and Mermin. And there's a line in that book which is very famous, at least famous to me. It says, "We shall have mercifully little to say about the 230 space groups, except there are more of them than one might imagine." Right? So we will not say much about the 230 space groups. And most real-world materials, usually don't require all 230 of them. There are statistics of space groups. Some are strongly favored over others. And most simple materials that we will study have just a small set of space groups. So in fact, what I'm going to do after this class, I haven't done it yet, I'm sorry, is I'm going to link, these are select sheets from the space group tables, and I'm going to put it on the Canvas website. I'm sorry I should have done this, but this is what I have, this big fat book called the International Tables of X-ray Crystallography, and this is what pages from that book look like. And it looks daunting to start with, but I will show you that it isn't really as scary as you think. Okay? By the way, another question I have, besides your familiarity with X-ray diffraction, have any of you used a tool called VESTA to draw crystal structures? Because that's going to be an important part of the next few classes. So I'm going to show you how to use VESTA, but maybe I'll teach you a few structures before we do that. I might try to get to it. Or what I might do is I'm not going to be here next week, so I may request someone else to come and do a little VESTA demo in the class. So if you have laptops that you want to bring to class, that will be useful. I'm sorry, but VESTA doesn't work as yet on iPads that I know of. Okay? You need a laptop. Can you emulate like OS X on an iPad? I have never seen anyone do that. That's not an iPad, right? That's a computer. Is that a computer? That's a computer. Yeah, that's a computer. Yeah. Okay, good. 3D. Let's start with the obvious thing to start with, the different unit cells. Right? And there are 7 different shapes of unit cells. In 2D, we discovered that every unit cell has to be a what? What kind of a geometrical object is every unit, every tile in 2D is what kind of a geometrical object? Parallel, a parallelogram. Every object in 2D that can tile 2D has to be a parallelogram. The opposite sides have to be parallel and equal. That's a parallelogram. In 3D, every object that tiles 3D space has to be a what in 3D? What's the parallelogram equivalent in 3D? And if you say it, you'll have to spell it. Any takers? Yes? No? It's this object. And I don't know whether I'm spelling it right. I don't know if there's an extra E there. So what does this mean? It's an object with 3 congruent faces and all opposite faces, 3 faces. It's an object with 3 arbitrary faces that are joined, and all opposite faces are congruent and parallel. So actually, it turns out that any 3 lines meeting at a point at arbitrary angles, let's call this A, let's call this B, let's call this C. We call this angle here gamma, we call this angle here alpha, and we call this angle here beta, right? And we say A is not equal to B, is not equal to C, alpha is not equal to beta, is not equal to gamma, and just for good measure, we say it's not equal to 90 degrees, right? Believe it or not, this object, if you close these off like this, right? I've made each of these planes a parallelogram, and then I close it off to get me an object like this. Do you see this figure on the screen? Believe it or not, you can tile 3-dimensional space with this. Even though it looks like it's really sort of ugly, you can actually tile three-dimensional space with this. So this is the most general cell. Most general, so 3D. Unit cells, and these are unit cells in 3D. This is the most general case, and it's called a triclinic cell. So any three-dimensional crystal can go into this one cell. So you may rightly ask, if we need only this one cell for all three-dimensional crystals, why should we learn other cells? Right? Is this a valid question to ask? Yes? The reason we use other cells is to specify this cell requires all these different variables, but a cube, for example, requires only one variable to specify. You just need the length of the cube. You know all the angles are 90, you know all the lengths are the same, so you just need one length. So crystallography insists that if you have a simpler representation, you should use it. Okay? So that's why we don't use triclinic cell for everything. We start off with cubic, which I don't need to tell you what a cubic cell is, where A is equal to B is equal to C, alpha is equal to beta is equal to gamma is equal to 90 degrees. And then we go tetragonal, where we elongate one of the axes. So A is equal to B, not equal to C, and usually C is greater than A is equal to B. Alpha is equal to beta is equal to gamma is equal to 90 degrees. And then there is orthorhombic, which is the case of the general box. Orthorhombic, where you can imagine A is not equal to B, is not equal to C, but all the angles are 90. Related to triclinic is monoclinic, where one of the angles is not 90. So it typically has a rectangular base, but one of the angles goes off, and this may not be. Yes, this is a typical cell. This is monoclinic. And typically in monoclinic, A is not equal to B, is not equal to C. Alpha is equal to gamma is equal to 90 degrees. Beta is not equal to 90 degrees. So how many cells do we have? We have 1 triclinic, 2 monoclinic, 3, 4, 5. We now need 6 and 7. So 6 is rhombohedral. And rhombohedral is a funny cell. It's basically a cube. So I'll draw it like a cube. But imagine that you take the opposite corners of a cube and stretch it a little. Imagine that you make a cube with wire. So the length of each edge is a constant. But then imagine that you take the opposite corners, any two opposite corners, and stretch it a little bit. And then you'll find that A is equal to B is equal to C, and alpha is equal to beta is equal to gamma, but it's not equal to 90 degrees. It's not equal to 90 degrees. That's rhombohedral. And then there is a cell that's called hexagonal, a popular cell. And in hexagonal, what you have is, we saw this also in 2D, gamma is equal to 120 degrees. So A, B, C. A is equal to B is not equal to C. C is long as usual. And alpha is equal to beta is equal to 90 degrees. Gamma is equal to 120 degrees. So it may seem like a lot, but it really isn't a lot. Have I made a mistake? What are you looking at?
Oh, just counting.
7. We have 7. Triclinic, monoclinic, cubic tetragonal, rhombohedral, cubic tetragonal orthorhombic, rhombohedral, and hexagonal. In fact, in practical terms, I can tell you that people only use 6 of them. Because it turns out that 3 rhombohedral cells can go into a hexagonal cell. All rhombohedral is equivalent to hexagonal. So the opposite is not true. You can't take hexagonal cells and make them rhombohedral cells, but every rhombohedral system, you can shove it into a hexagonal cell. Okay? So these are, what have I just enumerated here? I have enumerated the 7 crystal systems. These are called the 7 crystal systems. From the 7 crystal systems, so I'm sorry, but I'm going to erase the board. Are you done? Or tell me when you're ready and I'll erase the board. This board is not very satisfying. It's not man-sized. I need a bigger board. A man-sized board. Can I erase? Yes? Okay. I'm going to erase because I'm just going to tell you now that these are the 7 crystal systems. And in addition to the 7 crystal systems, you have centering on some of them. And that gives you the 14 Bravais lattices. Okay? So crystallography, there is quite a bit of terminology to be learned. But if you've heard the term crystal system, you can hear the term Bravais lattices. So 3D, 7 crystal systems. Crystal systems plus centering is equal to 14 Bravais lattices. What does centering mean? So for example, this would be called P cubic for primitive. Let's say there's an atom in the corner, it stays in the corner. Then you would have I cubic, where an atom in the corner, the same atom goes to the center, and you have F cubic, where you have an atom in the corner goes to the centers of all the faces. Okay? So those are examples of centering. You may remember that in 2D, you had one kind of centered lattice. It was called centered rectangular. And the atom in the corner of the rectangular lattice also went to the center in that case. In the cubic case in 3D, you have 3 kinds of centerings. For orthorhombic, you have 4 kinds of centerings. Tetragonal, you have 2 kinds of centerings. So different crystal systems have different amounts of centerings, the different kinds of centerings. So this adds up to 14 Bravais lattices. And I will not go through this in detail here because I'll show you this when I show you crystal structures. I'll show you that this corresponds to the element alpha polonium. This corresponds to, for example, alpha iron. And this corresponds to, for example, copper, silver, and gold. Okay? And of course, we also call this simple cubic. Simple cubic. We call this body-centered cubic. And we call this face-centered cubic. Face-centered cubic. Okay? And these things, and a lot of these things are best illustrated when we're actually studying crystal structures. So, at least for me, I can tell you that I've always found crystallography on its own, at least when I taught it, I found it somewhat like a dry subject. Because I'm not interested in crystallography, I'm interested in crystal structures. I'm interested in knowing where the atoms are. Right? Crystallography is the mathematical construct. So if I take the space group tables, the space group tables doesn't tell me where the atoms are. So to fully appreciate this, I think we need to learn some history. Crystallography is completely a mathematical science. And the 230 space groups had already been counted by an American crystallographer called Barlow and a Russian crystallographer called Fedorov. These were really mathematicians. We call them crystallographers today. They didn't call themselves crystallographers. They called themselves mathematicians, right? So, and just to remind you, in the middle of the 1800s, there was no internet, there was no television, so people could actually spend time with pencil and paper and figure out that there were 230 space groups, right? They were bored, they had nothing else to do, right? We're grateful to them now, but when you think about where they were in life, like obviously, very likely they also had to work in daytime because there was no power, there was no light switch at night. Okay, so these guys figured all this out purely mathematically, and this is important to know. Then when did we start thinking about the structure of matter? People didn't properly appreciate the existence of atoms. There were people even in the early 1900s, 1920s even, who didn't believe in atoms. They said, I don't believe in atoms, I can't see them, right? But people started really buying into the idea of atoms, etc., say around 1900s, right? What happened in 1895? A German scientist called Röntgen discovered or invented. I think you could say either. But he invented a way of generating X-rays. And you know the famous Röntgen experiment, right? He was playing around with cathode ray tubes, basically vacuum tubes with electrodes, and he was passing currents through them. And we're told that he had a crystal of a special material, barium hexacyanoplatinate, also called barium platinocyanide, lying around in the lab. And he found that this crystal all of a sudden started glowing when he turned on the cathode ray tube. So he knew that there's some invisible radiation going from the tube to this crystal that was exciting it and making it glow. Today we'd call it a scintillator crystal. It's actually interesting because not a lot of materials glow when exposed to X-rays, so he was lucky to have one of these around. Soon after, people were clever enough to figure out what the wavelength of X-rays were. And they knew that these wavelengths must correspond to the spacings between atoms and crystals. So how did they know that? Before you know the structure of matter, how do you know before you have a way to probe the structure of matter, how do you know the structure of matter? Sorry? That's a very good, that is a brilliant answer. That is actually exactly correct. And in fact, one of the first people to do that was actually Johannes Kepler. Do you know who Kepler was, right? He was the scientist who came up with the laws of planetary motion. So Johannes Kepler, working in the 16th century, worked on two things. One is he worked on the so-called close packing problem. How do you pack spheres so that they're close to each other? And we'll come to that. The other thing he worked on was snowflakes. If you've ever seen snowflakes, I'm told right now you'll see a lot of them in the East Coast. Snowflakes are all six-cornered. By the way, if you're a stickler, you'd not call this a snowflake, you'd call this an ice crystal. Apparently, that's not the same thing. And if you actually look at snowflakes, they're not just six-cornered. They have these, often they have fractal patterns. They repeat themselves. But you know that every snowflake is every ice crystal is six-cornered. And so Kepler actually wrote this document that was titled, a study, if you like, on the six-cornered snowflakes, and Kepler actually figured out that the external structure must reflect the internal arrangement of whatever species built it up, right? So these kinds of things people had started recognizing. And there's actually a simple experiment you can do with coins. If you took a lot of coins of the same size, let's take a coin, let's assume that that's a coin, that's a coin, that's a coin. I'll draw one more for good measure. And then I'm going to make another layer of coins, and I'm going to push it up against this. Would the next layer sit like this? Or is there a better way to arrange it? Is there a better way? If I push the coins in the second layer up, what would the coins do? They'd slide. You agree that they would be happier looking like this. They'd be happier looking like this. Right? And if you have another layer of coins, maybe it looks like this. Right? And if you keep doing this, you notice something. If you have a long layer like this and a long layer like this, you notice all angles in this arrangement, all angles are 60 degrees or 120 degrees. There are no other angles that you get from this kind of an object. You can verify this for yourself with a lot of coins. Or you can draw a lot of disks, say in PowerPoint, and just stack them against each other like this. You're guaranteed to find that you only find 60-degree angles and 120-degree angles. You won't find any other. So the external shape of the object may tell you, even if you can't see the individual internal constituents, the external shape may tell you what the individual constituents are. So it turned out that people already knew the structure of things like sodium chloride. They had been able to guess the structure of sodium chloride even without any technique to look inside it. What would you need to get to the structure of something like sodium chloride without knowing the structure inside it? You would actually need to look at the shape. And all of you have seen crystals of sodium chloride, right? Salt crystals, they're perfect little cubes. Take a little perfect cube of salt. You know its weight because you can weigh the mass. Do you know how many sodium and chloride atoms there are in that little crystal? Yeah, 1:1, yes. That you can even guess because you know the charges, right? But do you know how to count? If I give you a little crystal of sodium chloride and I ask you, tell me how many atoms of sodium and chlorine there are in this. Do you know what experiment you do to determine this? It has to be an experiment that existed in the middle of the 1800s. How can you count the number of atoms in a little grain of sodium chloride? And you can't say mass spectrometry, crystallography. You can't use modern techniques. You have to use old techniques. Do you know how people counted atoms in the old days or ions in the old days? Have you heard of colligative properties? If I take sodium chloride and dump it, if I take that crystal of sodium chloride and dump it into a known amount of water, I get a salt solution, yes? Can you tell me something about the freezing or boiling of the salt solution? The freezing point goes down, the boiling point goes up, and you know that you can use the boiling point elevation to determine the molality of the solution. Right? So people knew how to do these things. People also knew how to determine the masses of atoms, individual atoms. So if you know the mass and the volume, you can measure the density. If you know the density, you know how far the atoms are from each other. If you know how many atoms there are in a certain volume, and you know that it's plus and minus, you know how to arrange them. So people were able to guess. In a nutshell, people were able to guess what the structures of simple materials were at the atomic level, even though they didn't have any direct atomic probe. So when X-rays came along in 1896, very soon thereafter, people realized that X-rays had wavelengths that compared to the spacings between atoms. Right? So in 1907, a German scientist called Max von Lohe was the first to hit crystals with an X-ray and to use photographic film to record what the X-rays looked like coming out. Okay? He won the Nobel Prize for this in 1911. But his paper was seen by a young William Lawrence Bragg, who was an undergraduate student in the University of Cambridge, when he saw the pictures that von Lohe had taken of X-rays going through a crystal of zinc sulfide, Bragg was able to recognize that the X-rays coming out looked like they had gone through, been reflected by mirrors. And he used this to say the planes of atoms in crystals act like parallel mirrors, and then he came up with the Bragg law, which is a very simple law, which made the application of crystallography very common. So, and he, as I said, he was in his early 20s, and he was not, at this time he didn't have a lab, but his father was a physicist, I believe in the University of Birmingham or Manchester, one of these two. So he wrote to his father, as children do. You know, children frequently write to their fathers or their parents to say, please can you build me an X-ray spectrometer? So he must have sent his father a postcard saying, Dad, no, he probably said father. In those days they were formal, right? Dear father, having read the paper of Herr von Lohe, I have a suggestion to make for an X-ray spectrometer to be built. Anyway, Daddy builds an X-ray spectrometer. They verify the Bragg law, and you know the Bragg law. So 2d HKL sine theta is equal to n lambda. They verify this law, and I believe in around 1916, very soon thereafter, father and son were awarded the Nobel Prize. And even to date, Bragg remains the youngest person, I think, I'm pretty sure, youngest person in the sciences to win a Nobel Prize. Oh, not the youngest person, because Malala Yousafzai is the youngest person. You know, she won the Peace Prize. This girl from Pakistan. So, as soon as X-rays became widely available, and as soon as people understood the utility of the Bragg law, they started studying the structure of materials, right? So that's the science of crystal structures. The science of crystallography is simply the mathematical construct. Why do we need crystallography? We need crystallography, the mathematical foundations. I've illustrated this with these notes. I don't know whether I've posted these notes. But here, for example, is the structure of a material called forgesite. Okay? It's just pure silicon and oxygen, but it forms in this complex structure, and it's a zeolite. Zeolites are used, for example, in kitty litter. They're used in a lot of applications, but one of the big applications they used in kitty litter. You know what kitty litter is? Why are they used in kitty litter? Because you don't want the kitty litter to smell, and these zeolite cages trap the molecules that would make the kitty litter smell. I'm having a hard time saying kitty litter. Anyway, you get what I'm trying to say. Okay? This structure is cubic. Its space group it has a space group. And the cell parameter of the edge of the cube is 24.56 angstroms. That's pretty big. For a crystal structure, that's pretty big. To give you an example, gold has a cell parameter of about 4 angstroms. This is almost 25 angstroms. So when you draw out the structure, there are something like there's something like 400 atoms that are needed to draw the structure. Okay? But when you do the crystallography, you find that the whole structure is defined by just the position of one silicon atom and 4 oxygen atoms. So the whole structure of forgesite is reduced to a very simple description because of crystallography. So the work here is done by crystallography. Okay? And this is probably best demonstrated by playing with the tool Vesta. So I will arrange for a class on Vesta where you can play with these things. Okay? And again, I would, if you don't already have it, if you could bring a laptop, I'll announce it. If you could bring a laptop, and if you could download Vesta in advance, It's from a Japanese website. It's free. It'll work on Mac or Linux or Mac, Linux or PC. Okay. Somebody has to write an iPad version. So that's my basic introduction to crystallography and how crystal structures are determined. They're determined by shining X-rays at crystals. And crystallography doesn't know crystal structures. Crystal structures require crystallography. This is an important distinction. Sometimes I will say, what is the structure? And people will say, orthorhombic. Orthorhombic is not a structure. Orthorhombic is a crystal system. Okay? Or I'll say, what's the structure? And they may give me the space group. They may say FM3 bar M. That's not a structure, that's a space group. The structure is the combination of where the atoms are, what the space group is, and what the unit cell dimensions are. So we'll start seeing that by looking at some simple crystal structures, right? And I apologize that I don't actually have these crystal structure tables at my disposal today. So let me actually turn this around. Maybe I'll start showing you crystal structures in the next class. Let me start with close packings, okay? And this is probably something that you're accustomed to. In fact, I already did a close packing here in 3D, in 2D. So let me start with close packings, and I will actually show you the corresponding crystal structures in the next class. So close packings are the packings of equal spheres to optimally occupy volume on three-dimensional space. So if you look at it from on top, if you have a layer of spheres like this, you allow them to touch each other. The next layer of spheres will come and sit like this. Okay? The third layer of spheres below will come and sit like this, etc. Right? Imagine that these are spheres. They look like this, but imagine that these are spheres. And by the way, in 2D at least, you know that the cell is going to look like this hexagon. Okay? What's a hexagonal cell in 2D? You may remember that I told you that it's two right triangles back to back. Two equilateral triangles back to back. So that's the unit cell. And if you tile it, you get what is called two-dimensional hexagonal close packing. Okay? And in 2D, there is no other better packing. It's unequivocal. You just shove all the atoms so that they touch each other. In fact, it's very easy to make such a packing. You just take a tray, put a lot of coins in it, and start, but the coins must all be the same size. You start jostling it around, and then you push it so that all the coins go and touch one wall. At least, that they're a single layer and they're touching a wall, and then you just shake it a little more and they'll automatically take on this packing. Right? The second layer on top, if you build a similar layer, the layer on top has two choices. It can be, if you look, there are these sites here. I'm going to put a red on alternate sites. These are alternate sites, red. These are red sites. And there are green sites. Right? So I can make a red layer that sits like this, that's centered around these sites. And if I put a red here, you know that this is a divot. This, I'm putting it from on top here, but it actually looks like this if it's coming from on top. So that red layer goes there, that goes there, that goes there, that goes there, that goes there, and that goes there. So that doesn't look very pretty. It's much easier to do on a computer. But here's the red layer. So if we call this the A layer and we call this the B layer, we can now put a third layer on top. The third layer can go on top of the original. So then we'd say it's AB, AB, AB. Or the third layer can now go on top of these green circles. And this is a different position. Right? This is a different position. So that would be ABC, ABC stacking. So if I have this kind of stacking, I call it cubic close packing. So this is ABC, ABC stacking. Cubic close packing. Or I can have AB, AB, AB. So I just skip the third site. This is hexagonal close packing. And this is the structure of magnesium, for example. Structure of magnesium and zinc and some other elements. This is the structure of nickel, copper, silver, gold, palladium, etc. This is also called face-centered cubic. So do you know how you show that cubic close packing is face-centered cubic? Well, face-centered cubic, I will show you the structure presently in the crystallographic sense, but the face-centered cubic structure looks like this. It's a cube with atoms at all the corners and atoms at the centers of all the faces. This is face-centered cubic. This is face-centered cubic. Face-centered cubic. But I can draw face-centered cubic in another way. If I want to show that this is the same as this, I have to draw face-centered cubic in this special manner, where I draw the back and the front of the unit cell like this. So I draw the unit cell so that if I hold the cube, I'm holding one corner of the cube on top and allowing the other corner of the cube to dangle. Do you see that this is a cube? Okay. Now if I take this cube and start decorating it with the corner atoms look like this. And the atoms at the centers of all the faces look like this. There's one at the back there. There's one at the front there. So these two are the same thing. These two are the same thing. I hope you are able to see that these are the same things. Now, if you blow these atoms up, you find that this is like an A layer. This is like a B layer. This is like a C layer. And this is back to being an A layer. So the ABC, ABC, ABC stacking of close packed spheres is reproduced in a cubic, face-centered cubic unit cell. If you look along the body diagonal, if you project down the body diagonal, which is the line that joins opposite corners, you see this ABC, ABC, ABC stacking. Okay, so I will show you FCC and I will remind you that FCC is the same as cubic close packing. Hexagonal close packing, I will remind you when I show you the structure of I'll show you the structure of magnesium. So our next goal is to look at some of these simple crystal structures and the crystal structures of simple elements. So it starts off, so let me in fact, even though I was not quite prepared for it, I didn't bring the notes. I will start off, it doesn't matter. I'll start off by showing you, and then we can catch up with the details presently. So the simplest crystal structure is alpha polonium. And you may say, what? In fact, where is my chemical engineering colleague who knows the periodic table? Is she no longer coming to class? So alpha polonium. Okay, so where is polonium? Polonium comes under oxygen in the periodic table. So it's oxygen, sulfur, selenium, tellurium, polonium. Why do we not see polonium in our everyday science? Because it's pretty radioactive, right? But we have to study polonium because it has this uniquely simple crystal structure. No other element has it. So do you know why polonium is called polonium? Who discovered it? Who discovered it and then named it for the country they came from? Poland. Who came from Poland? Hint, lived in France, but came from Poland. Marie Curie, right? Marie Curie. Marie is actually her French name. She was actually, in Poland, they'd call her Mania. Mania Sklodowska became Marie Curie. Curie was, of course, the man she married. So Marie Curie discovered polonium. And famously, she discovered polonium on the way to finding the element radium. So it's really a fascinating story. First, she and her husband and someone called Henri Becquerel discovered radioactivity. They discovered that certain rocks that were pulled out of the earth could emit radiation that could darken photographic film that was put away. So again, it's, I think, a serendipitous, an accidental discovery. The story goes that they had some photographic paper or photographic plates that were sealed, light sealed, but they had put a rock on top of it, a radioactive piece of rock. And then when they came and, for whatever reason, developed the film, they found the film had been exposed even though there was no light radiation hitting it. So it was this invisible stuff coming out of these rocks, okay? And by this time, they already knew about X-rays and so on. So they knew that some radiations could be invisible. Today, we know this as radioactive decay from the rock, right? And specifically, they had this ore that they got from Austria, and pitchblende had the element uranium in it, which I think was already known. So both pitchblende and uranium, they quickly discovered, were associated with radioactivity. Pitchblende was the ore of uranium, so uranium was extracted from pitchblende. So they were surprised that even after the extraction of the uranium, there was still radioactive stuff left. And in fact, pitchblende was more radioactive than the uranium. So they knew there were other elements, other things to be found in the pitchblende. And that's how they discovered polonium and radium. Right? And you know, Marie Curie won. So first they got the Nobel Prize. Marie Curie, Pierre Curie, and Henri Becquerel got the Nobel Prize for the discovery of radioactivity, and then Marie Curie got the Nobel Prize in chemistry on her own for discovering these elements. And how she discovered these elements is like a story of, it's a remarkable story. She apparently manually processed about 1,000 kilograms of more of this element pitchblende by boiling it in concentrated hydrochloric acid. And then extracted it very patiently. So radium comes under barium. So just like barium forms an insoluble sulfate, radium forms an insoluble sulfate. Was all this work with radioactivity good for her? No, it killed her. It's widely believed that she died of it. It's also thought that her daughter died of it. And in fact, at that time, a lot of these early researchers were exposed to too much radioactivity. And somebody's told me, I haven't verified this, but someone's told me that if you go to France and you go to Marie Curie's office, which is now like a museum, you can't actually enter. There are like sheets of plexiglass that prevent you from going in because it's too hot. It's too radioactive. So polonium, this funny element that comes in the right-hand corner of the periodic table, there are not a lot of known modern uses for it. The only one I can tell you from the top of my head is that the KGB or the GRU or whatever, the Russian Secret Service, uses it to kill people it doesn't like. So famously, they've used it against people in some parts of the world. In the UK, for example, they used it to a Soviet spy defected to the UK, and the Russians tried to kill him. Or maybe they succeeded by feeding him a little polonium. It's tasteless. You don't need much of it to kill you, and it is a relatively safe radioactive element. It's an alpha emitter, so you can even just put it in a plastic vial, and the radiation doesn't leave the vial, so you can carry it around. But why do they use it? They could use other things, right? Why do they choose to use alpha polonium to bump off people? Other than the fact that it's easy to transport and it's tasteless, you don't need a lot to bump off someone. Why do you think they use it? Any clues? You want to guess?
Let them know they want to kill.
Exactly. It's a calling card. You can't just go to the CVS or the Walgreens and say, can I please buy a microgram of polonium, right? So it's a calling card. You know that only one person in the world can probably arrange this, can organize this. Or let's say maybe more than one person can organize it, but only one person cares to. That's our friend Vladimir Vladimirovich, okay, otherwise known as Putin. So polonium has this very simple structure, and the structure is simple cubic. So the space group is PM3 bar M. PM3 bar M. And I'm sorry again that I didn't make the space group tables available to you. I will make them available to you after class. But if you look at the space group tables, let me get out PM3 bar M. Here. PM3 bar M looks like this. It runs into 4 pages, but I think I need only these 2. It looks like this. And if you look at PM3 bar M, it says right against PM3 bar M, it says the full description of the table is P4 by M, 3 bar, 2 by M. 4 by M, 3 bar, 2 by M means there's a 4-fold axis, there is a 3 bar. What kind of a symmetry element is 3 bar? It's a rotation plus an inversion. It's a roto-inversion. 4-fold axis with a mirror, mirror perpendicular to it, a 3 bar, which is a roto-inversion, and a 2-fold axis. When you see 4, 3, 2, or even when you just see 4 and a 3 bar, you automatically know it's a cube, right? A cube has a 4-fold axis, yes? Joining one face and going, does a cube have a 3 bar? The 3 bar of the cube is again this axis here. That's the back face of the cube, the front face of the cube. This axis is a 3 bar axis. Right? If you look at the top 3 faces, you rotate them by 120 degrees and you flip them by a mirror. You flip them, you invert them through the center, it's a 3 bar axis. So this automatically tells you it's a cube. What does the P mean? The P means it's primitive. It means that if there's an atom specified, that atom stays where it stays. Okay? So the full description of the structure requires you to say what the A parameter is. And the A parameter, as I remember, is something like 3.9 angstroms. I'd better verify this, right? I'd better verify this, but it's somewhere there. And how do you determine this? Will this information be in the international tables of X-ray crystallography? No. This is determined by actually doing an X-ray experiment, right? So you also have the atom. So you have the polonium atom. And if you look at the structure description, it'll say something like polonium 1A, and it'll tell you 0, 0, 0. That's the position, XYZ position of polonium. So this whole thing is the crystal structure description. You need the identity, you need the space group, you need the cell parameter corresponding to the space group. Because it's a cubic space group, you need only one parameter. And you need to know the position of the atom. Now, for the first few structures I'm going to show you, the atom is always at 0, 0, 0. You'll see that. What is this 1A? This is called a Wyckoff multiplicity. And this is called the Wyckoff label. So these are named for an American crystallographer called R.W.G. Wyckoff, who apparently specified all these things in his PhD thesis. And to tell you what these are, so these are different identified positions in the space group. So if you had these tables here in front, which I will make available to you, you'll discover that 1A is 0, 0, 0, 1B is half, 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 3C is 0, half, half, 3D is half 0, 0, 6E is x 0, 0, etc. So these are all different positions in the space group. Okay? These are called special positions, and these are all different positions in the space group. And the space group, any space group, can have a general position. The general position here is XYZ, right? It could be XYZ, could be 0.237, 0.456, 0.679. That could be XYZ. It's always something between 0 and 1, right? It turns out that if you place in the space group an atom at the general position XYZ, it goes to 48N. Symmetry means there are 48 replicas of that atom produced. If you place the atom at 1A at 0, 0, 0, there are no replicas produced. If you place it at 3C, 0, half, half, then that atom gets reproduced at 0, half, 0, half, 0, half, and half, 0, 0, etc. Okay? So I'm going to well, I'll just leave this here. You guys are sitting too far apart for me to try to circulate them, but I'll post these on the website. By the way, if there is password protection on these PDF pages, the password is always going to be perovskite. So please write this down, Perovskite. In the past, I'd post them publicly. I'd post it publicly. No, now it's posted on Canvas, but when I posted it publicly, because it's proprietary, I didn't want to give it to the world. You have to actually pay to subscribe to it. Okay, so with this information, I can draw the structure. And the way I draw the structure is I draw it in sections. And this may seem a stupid exercise for something so simple, but I draw it as sections. I draw a section at Z is equal to 0. And because it's a crystal, Z is equal to 0 is always equal to 1. Okay? Imagine that this is X and this is Y. So the position 0, 0, 0, the third 0 is already taken care of. This 0 is this 0. Right? So 0, 0 means the atom goes here. And that's all. That's the whole crystal structure. But whenever we put an atom at the corner, we also complete the atoms here. Right? So this is the section at Z is equal to 0, and the section at Z is equal to 1 is also the same. So the crystal structure looks like this. It's a cube with atoms at all the corners. Right? And the edge of the cube, as I said, the edge of the cube is approximately 3.9 angstroms. That's what I remember it as. Again, I'll verify this, 3.9 angstroms. Right? So this is not a popular structure because it's mechanically unstable. It's not a very efficient way of arranging atoms together. And the reason that these atoms want to take on the structure is the special chemistry of polonium. It's actually got to do with something called relativistic effects. It's very sophisticated reason for it to take on the simple structure. But no other atom no other element in the periodic table takes on the structure at ambient pressure. It might take it on under some special conditions of pressure and temperature, but room temperature, ambient pressure, this is the only compound that we know that takes on the structure. Okay, so I'll wrap up now, and in the next class we'll do a few calculations of what the density, packing efficiency is, how to relate the radius of the atom to the edge of the cell, all of those things. Okay, and I'll go back now and post all these notes so that you can also look at them, including the space groups. Yeah, so when I post the space group tables for the next class, please download them and bring them on your computers or iPads so that you can look at them in class. That'd be very useful. And yeah. So, and anticipate that maybe I won't put up an assignment today. I'll skip putting up one today and put one up on Wednesday because I'd have covered more ground by Wednesday.